DACs are often used to generate a bias level in multiple applications, with the most popular being a set point control level or reference level. This is where the DAC is used to generate a precision DC output voltage or current, which can be used to provide a known DC input level to a more complex circuit. We will look at this in more detail with some specific examples. In this bias generation example, the DAC output is used to set the reference voltage level for a comparator, and the second input terminal to the comparator is connected to some variable signal, which could, for example, be supplied from a sensor. By varying the DAC output, the trigger level of the comparator is moved upwards or downwards. Effectively, the input signal is being compared to the DAC reference value, which is generally preset or predetermined, and the output toggles depending on whether the input is above or below the DAC reference voltage. The example shown here features a resistor divider network. So the set point is proportional to the resistor network used. A resistor divider network may be used in a case where the DAC output span is greater than the sensor output span. For example, if the sensor had an output span of 200 mV, but you were using a 5V DAC, the resistor divider will enable you to reduce the DAC output span to match the sensor range, which effectively improves your resolution in the process. In general, you want to keep the set point at the center of the sensor range. It should be noted that if you had a 5V DAC and a 5V sensor output, you may not require any resistor divider network. So what type of DAC is best suited to this application? The nano-DAC products are ideal candidates, being low voltage single supply DACs with a variety of resolutions, channel count, and interface options, making them easy to match to varying set point output needs. The nano-DAC family also includes integrated reference options, which will reduce the number of components needed, and the reference can also be used elsewhere in the circuit if required. The resolution of the DAC provides the granularity with which you can set the reference level. A 12-bit DAC has 4096 possible levels. The linearity of the DAC, that is its INL specification, gives the deviation between the ideal DAC output voltage and the actual value set by a particular part. The lower the INL, the more accurate the converter. In general, set point applications are 12-bit in nature, but some can require greater resolutions up to 16-bit. In this case, they do not require 16-bit accuracy, and hence INL of 8 or more LSBs may be sufficient. In multiple set point applications, a dual or quad-channel DAC might be needed. Some things to look out for are area-constrained applications where ADI's smallest packages can bring an advantage over competition. There is also our breadth and depth of portfolio to highlight, ensuring we have a match for the exact customer needs in terms of resolution, accuracy, and channel count. Here, there's a slightly more involved signal chain, but the underlying concept is the same: set point trigger level control. In this case, the application is a specific example of digital signal oscilloscope trigger level control. Again, the DAC output is used to set the reference voltage for a comparator. The DSO's input signal, after filtering and before the ADC, is connected to the other comparator terminal, and varying the DAC output will vary the comparator's trigger level. In this application, the output of the DAC is often buffered to realize the required output range, as the trigger level can be up to 10 volt or bipolar in nature. This means that if a low voltage nano DAC is used, then some additional buffering and gain scaling will be required. The DAC output can require gains of up to 5 to increase the span of the scope inputs. Bipolar DACs are a preferred option for this application, as high voltage outputs over 5 volt or bipolar outputs are often required when setting DSO trigger levels. The bipolar DAC portfolio offers user-programmable DACs with both unipolar and bipolar ranges from 0 to 5 volt, 0 to 10 volt, ±5 volt, and ±10 volt. Because of the flexibility offered in the output ranges, these parts are very portable across systems, being easy to design in and modify for other future designs with slightly different requirements. All that is required to change the output range is to change one bit in the control register. This means the hardware and layout can be reused across systems without the need for modifications. Similar to the Nano DAC family, there are versions of these products with and without a reference, with the R symbolizing a reference is included. For DSO trigger level setting applications, 16 bits of resolution is generally required. High accuracy is not a key feature, with 4 or more LSBs of INL being sufficient. There is no demand for DACs with high channel count, being single or dual channel products preferred. Something to look out for here is the trend towards faster settling times and also high resolution. Previously, 12 bits would have sufficed in these applications, whereas now 16 bits may be required. A DAC can be an ideal choice for driving MOSFET transistor devices, whether they are standard or power devices. At its simplest, the DAC effectively sets the gate voltage and is thereby used to turn on and off the device, allowing a drain source current to flow. The example shown here on the slide is slightly more involved and is a more common example from the communications market, where DACs are used to set the DC bias level of an LDMOS transistor. LDMOS transistors are used for RF power amplification, where the transistor is used to convert a low power radio frequency signal into a larger signal of significant power. These transistors need very good linearity to maximize the data throughput in a given channel. The main consideration to achieve that linearity is the DC biasing of the transistor for optimal drain current for a given power output. This means the bias needs to be changed to compensate for any small changes in temperature and lifetime drifts, retaining a constant output power. The aim here is to keep the transistor operating in the linear region. This DAC is used to retain the same operating point for the transistor. This highlights the value of the DAC for the bias generation, as it gives sufficient granularity to control the bias level accurately. Depletion mode devices are also used in similar applications. Depletion mode devices are biased negatively rather than positively and are potentially more power efficient than LDMOS devices. Given the need for a negative bias, a DAC which can output negative voltages, like one of our bipolar products, is required. The bias voltage required in this application is typically between 0 volt to +5 volt, so low voltage single supply DACs such as Nano DACs are a good fit. For depletion mode devices, the most popular DAC option is bipolar DACs, which offer the negative voltages. Digipods are also considered and used for transistor biasing, for which an extensive portfolio of digipods with and without memory is available. DAC resolution for granularity of the bias level is typically 12 bits, but 10 bits may also be sufficient. Single or quad DACs are mainly used. Also to note that often the preferred interface option here is I2C rather than the standard SPI. As the biasing of power transistors with the DAC is designed to compensate for drift, a temperature sensor is normally required in the signal chain. Some of these applications can also be space constrained, so our small packages may provide a key advantage here.